let's look on page 402. How to determine these areas. Okay, so let's choose a graph. So let's say approximate the area under the following graph. They already graphed it for us. They already gave us the picture. They already established from 1 to 6, 1, 2, 3, 4, 5, 6 subintervals. So in this case, n is 6. So let me write this down. So I'm on page 4. So this is 19, okay, on page 402. And we have n equals 6. From 1 to 7, so the interval is from 1 to 7. Okay, the function is f of x equals 1 over x squared. By computing the area of each rectangle to 4 decimal places and then adding. Notice they're not telling us what to do, but when we look at the graph, we know exactly if it's the leftmost point or the rightmost point. So look at the graph and identify whether we are estimating using the leftmost point of the subinterval or the rightmost point of the subinterval. The height will tell you exactly if it's left or right. The height of each subinterval. Anyone, please?
The leftmost?
Yes, absolutely. Because the height is right here. Base times height plus 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 base times height. Excellent. Good. So then the area A6, 6 left will be, what is the base? It's between 1 and 2, 2 and 3. So there again, the width or the base of each rectangle or subinterval if you want, the rectangle on each subinterval is 1. So I'm going to put it 1 so you understand it. It may not be 1. So then we have f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5 plus f of 6. I have to stop. I cannot have more than 6 subintervals. Do not go to 7. Okay, that would be incorrect. 1, 2, 3, 4, 5, 6. So therefore, all I have to do is plug them in a function. So I have 1 plus, because it's 1 over 1 squared, 1 plus 1/4 plus 1 over 9 plus 1 over 16 plus 1 over 25 plus 1 over 36. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Please remember that. So I will approximate this by adding them with the calculator. There is a nicer and easier way, and I will show you how to do that. But for now, 1 plus 1/4 is 0.25 plus 1 over 9 plus, I didn't mean that, plus 1 over 16 plus 1 over 25 and finally 1 divided by 36. This is what I want. 1.4914, approximately 1.4914. And this is how we estimate the area under a graph. Now, question. Just a question for you. We used n equals 4 in the previous example. Here we used n equals 6. What if I use n equals 128? What if I go to n equals 1,000? And what if I go to n equals 10,000? What if I go to infinity? And you can say that's not possible. So forget infinity for a moment. Which of these approximations will be the best? The most accurate, the closest to the exact? let's take a look. So with n equals 4, I have this. With the leftmost point. But what if I have, it's even difficult to graph, right? What if I have a 10,000? Of course, I don't have 10,000 here, but I cannot make them thinner than this. Which one will be the better approximation? 4 or 10,000? It's okay if you're wrong.
So I know 4 would be easier to calculate.
Correct. But which one will be closer to the exact area?
10,000?
Of course. The bigger the number, the better. The less overestimation or underestimation. And we say, okay, now let's talk about when n approaches infinity. You can say, is that possible? No, but we have a concept, and the concept is the concept of the limit. When the number of subintervals approaches infinity, of the sum of areas. Because that's what we are doing. We are summing areas. Base times height plus base times height plus base times height. This is sum of areas of rectangles. So if we make this, the number of subintervals increase without bound, and we add the sum of the areas, we add and we add areas, and we add, this is guaranteed to be exact. Because there is no leftover and no overestimation. We make the number of subintervals increase so much that there is not going to be an overestimation or an underestimation. This will be exact. And no, don't get scared. We're not going to do this. We have a different notation. With my STEM class, we do this on different polynomial functions, but there is no need here. Okay, so the exact area, of course, like we had this symbol for the most general antiderivative, we have the same symbol for the area, slightly different. The exact area will be the definite, not indefinite integral. The definite integral, why is it definite? Because it clearly says from this to this, definite, not indefinite. It's not the most general antiderivative. So it's the definite integral from a to b from f of x dx. So the exact area is the definite integral from a to b from f of x dx. So let me put them together. The most general antiderivative is the indefinite integral from f of x dx. Now, please remember, very important difference. This is a number. This is a number. This is a function. Basically a family of functions. Huge difference. Huge difference. The definite integral will give us a number. The indefinite integral from f of x dx gives us a family of functions because it gives us the most general antiderivative. Now, how do I calculate that? Okay. There is a formula for calculating definite integrals. So let's write it. The integral, the definite integral from a to b. What is a to b? Is this interval. A to b is this. A to b. What was on in our example? This is a to b. 0 to 4. Okay, so the definite integral from a to b from f of x dx is the most general antiderivative is normally denoted by uppercase f of x. This is a function, this is the antiderivative. A vertical bar from a to b equals, I evaluated when I plug in b, and I have to subtract when I plug in a. So this is part 2. It doesn't matter, 1 or 2. So this is the fundamental theorem of calculus. The fundamental theorem of calculus. What does it say? It teaches us how to find a definite integral. How? Find the most general antiderivative, and when after you found it, plug in the upper limit, and then subtract when you plug in the lower limit. I want to practice this first on several examples, and then we'll look at word problems and everything else. So I'm going to share my screen. On the previous page. Anything you like to choose. I'm going to choose 11, and then you choose the next one. So the definite integral from 0 to 6, from 2x plus 3 dx. Let's see how we calculate this. Okay. So first of all, I have to find the most general antiderivative. In this particular case, there is no need for c because this will be a c and this will have a minus c. That's why the two c's go away. So when I determine or evaluate a definite integral, there is no need for c. Why? Because the result is a number. The result is not a function. Okay. So now I copy 2, and then I am asking myself which function I differentiate to get x. Which function I differentiate to get x. Is anyone with me? Please.
Yes. I'm not sure which one. I'm not sure what you would do there.
Okay, let's take a look at the... Good. Very good. Remember that? Yes? Plus? Which function I differentiate to get 3?
3x.
Very good. No need for c. Put everything in parentheses, a vertical bar, and copy 0 to 6. We haven't finished. Here is the end point. In this function, of course I'm going to simplify. In this function I plug in 6, and then I subtract when I plug in 0. Luckily for me, when I plug in 0, I get 0, so in this example there is no need, because the lower limit is 0. So when I plug in 6, I get 36 plus 3 times 6, 18. If you want, minus parentheses, plug in 0, you get 0, plug in 0, you get 0. 36 plus 18 is 54. So the definite integral from 0 to 6 from 2x plus 3 dx equals 54. Because we know now the fundamental theorem of calculus, I want to go back to our example, this example that we started with, where we said we wanted to find the approximate area, because we didn't have all the information when we started half an hour ago, under the function f of x on 4, 0 to 4. But now we know how to determine it exactly. We're not approximating it. Now we can know how to find it exactly. Can anyone help in setting it up? So the function is x squared plus 1, and the interval is, which page am I on? Am I on 6? I'm on 6. So the function is f of x, x squared plus 1. The interval is 0, 4, and we want to find the area, the exact area. Anyone would like to dictate how to set it up? It's okay if you're wrong.
So you do the integral,
The definite integral, very good, awesome.
4 will be at the top and 0 at the
Yes,
bottom.
we say from 0 to 4, from 0 to 4, very good, from
And would the 1 go first?
from the function. I have to write the function,
Oh, x squared plus 1.
dx. No integral without dx. Or if it's t, dt. If it's u, du. If it's w, then dw. Good. Perfect. Which function prime is x squared? Which function we differentiate?
X cubed over 3.
Excellent. Which function I... Yes,
X.
excellent. Close everything from 0 to 4. Luckily, they're polynomials. I mean, it's a polynomial function. When I plug in 0, there is no need, but I have to start with 4. 4 to the third over 3 plus 4. 4 to the third is 64 divided by 3. 3 times 4 is 12, so 64 plus 12 divided by 3. So this is 76 divided by 3. Remember what we found? With not a very good approximation, we found that the area is somewhere between 18 and 34. This number has to be between 18 and 34, guaranteed. So when I divide, I don't have to, I just wanted to share my screen with you. It's 25, as expected, 25.333. So as expected, this is the exact, this is the underestimation, and this is the overestimation. This was with the leftmost point, this was with the rightmost point. It doesn't mean that always and all functions will have an underestimation with the leftmost point and an over with the rightmost point. It depends whether they are increasing or decreasing.